Hey, what's up, guys? Yeah, so in this video that we need to keep proving this theorem about solovay and Baker and Grill. So basically, you need to find oracle B such that NP and P are at this oracle space is not is different. And the proof is complicated, so let me just tell a story which is introduced by Terence Tao, and I will also post the link below. I think this article is very good that they give you the intuition how to find this B. Okay, so previously we introduced A to be super powerful language, right? So in this case, in order to separate them, we should make B. So we should make B to be very restricted. Okay, so the idea is that imagine there is a computer, and this computer the only thing this computer is oracle B. Okay, and the only thing you can do is just put some URL. Okay, so put some character, and in this computer, and click it, and this computer can only check some local file. Okay, so and so if your URL is wrong, then you always get nothing. Okay. Okay, and this computer is for each length n. For each integer n. Okay, sorry, for each integer positive integer n, and there's only one URL. So imagine that so for each n so there's a possibility that 0, 1 to n. So total we got 2 to n, and so there's only one URL. There's should be sure. So like for each n, there's only one. There's at most one URL, which is in 0, 1 to n, with length n is correct. At most one, and may or may not. So there may be a case that there's no such URL. Okay, so there's no such URL. Maybe there's a case there's no such L for that's n. Okay, so this is first one. And second one, URL has no meaning. Okay, so this is like so the procedure, the way to construct such URL is like for each n. So we just randomly flip coin. So if coin is head, then we just randomly choose. Let's say we choose A belong to 0, 1 to n to be the answer, to be the correct one. Okay, and then if coin head tails, then do nothing. Okay, that means that for if you get tails, then you get nothing. Okay, so there's no such URL, and the only thing you can do is just plug some URL in this B, and then see whether if you got 404, that you can do nothing, or you can just try another. Okay. Okay, so the idea is that the simple checks that you can claim that at least it's not rigorous proof, but almost already get a feeling. So it's like NP, right? So let me just ask a task. Okay, so we define a task. So task is that the given n determine whether there's an URL with length n. Okay, so this is task. That's denoted this has to be L. Okay, so fact is very trivial to prove is L in NPB. Okay, because very simple, right? Because for NP you don't NP NP doesn't need to do any calculation, right? So you just there is a certificate. A certificate just URL, okay? And the URL length n, so NP just plug his URL in the computer. So just access Oracle B. Okay, but you can think a little bit and see that L should not in PB, right? Because P cannot guess. Okay, so the only thing is that P almost need to verify every string with length 2 to the n, And the only thing P can do is just plug this into the oracle B. So even P can access oracle B, P still cannot solve it, right? Because P need to plug one by one. Okay, and there's a worst case that there's no such UI. Okay, so which you can see that PB is different from NPB by this simple argument. Okay, but I think this is not a proof that you usually see a textbook. The textbook proof is not like this. Okay, so let's present a textbook proof. Well, the textbook proof is much more difficult, and textbook proof is much more difficult. Okay, so the idea is that so let me just give a notation. So this notation is very bad. So notation is that given decision language L. So L is a decision language. You can define U to the L to be 1 to the n. So 1 with less n. If so URL is another language, right? Such that 1 to the n is the answer if there is a x belongs to L and the x is less n. Okay, so this question said given any language, you ask if there is an x with less n is correct in that language, then you define another language or define another set which is 1 to n. Okay. Okay, so you can view also one can view, right? So one can view L as an oracle. Okay, so basically I can let L to be B, right? Because the oracle you can view oracle as a language, right? Because you just ask as oracle. So if oracle tell you yes, that means that that's yes in that language. So you can view oracle as B. Okay, so that obviously that for any oracle, UB is in NPB, right? Trivially, because for NP you just check where 1 to the this is in check 1 to the n is check there is a certificate, right? Since you can access oracle B, so NP can just directly solve it. Okay, so the problem is that we need to construct oracle. We need to construct oracle B such that P to the B such that UB do not belong to P to the B. Okay, we need to construct such oracle. So the difficult part is how do you construct such oracle? Okay, so previously the oracle is defined to be like use the very simple intuition that you can construct P. But in a rigorous proof, you need to use the diagonalization. Okay. Okay, so first, so we need to right. So let's say for every I, so very integer I, we define mi to be the. So we know that the Turing machine is countable, right? So Turing machine is countable. R's are countable. Okay. So actually, let's say so Oracle Turing machine is also countable for given Oracle, right? So we can for every I, we can define MIB. We can define to be MI to be the Oracle Turing machine. So Oracle Turing machine. So each I will label a Turing machine. And okay, so at each stage, so each stage I, okay. So we want to make sure that this MI B or just Oracle B does not decides UB let's say in 2 to the n divided by 10 steps. Okay. This is the floor notation. Okay. So this idea is a little bit tricky. Okay. It's a little bit tricky. So let's see how do we say things. Okay. So okay, so for each stage I, right, MIB does not decide you'll be in 2 to the n steps. Okay, so this is just this. This is basically I will describe it in detail. So next things is that we need to Okay, so let's say you already decide for some I. You already decide for like say M1 and 2, maybe up to MK. Let's say you already you already decide. You already construct such UB. Okay, so yeah, you can try to prove. You always construct such UB. Okay, so now you can choose. So now you want to choose the next, right? So for K+1, you will choose N to be large enough. Okay, and then you just run mi, let's say mi on the 1 to the n inputs for 2 to the n divided by 10 steps. Okay, you can freely assume that n is equal to equal to 4. Okay, so choose n large enough, and you just simulate mi on 1 to the n for 2 to the n divided by 10 steps. And okay, so if mi, so there's a case, right? So there may be a case that mi query, so there may be a case that mi queries some string, right? Some string in the so mi may carry some strings. Will query some string ask for oracle, right? But mi at most take 2 to the n divided by 10 strings. Okay, and we will make sure that whenever this mi query that kind of that length and then length whatever string in whatever length in these 2 to the n divided by 10 steps, then we just say these strings do not belongs to B. Okay, so we will just brute force. So any string in queries is R9B, or we just brute force. Make this all this string 9B. Okay, so this is like a stupid. Okay. Okay, and yeah. Okay. Okay, and so finally mi will stop, right? Because mi take 2 to n steps divided by 10 n steps. Okay, so okay, so if mi accept, so if mi accept on this 1 to n, then I force, so I can force 1 to n 9b. Okay. Okay, and if mi accept and mi reject on 1 to n, then I just force what? I just force for some list length n, I just choose that n choose random bit string 0 1 to n belongs to B, but 0 1 to n are not query before, not query before. Okay, and this is possible because we at most we take 2 to the n divided by 10 string, right? So there should be plenty choice. So we just randomly choose 0 1 to B, but 0 1 any are query before. Okay. Okay, so by this construction, that you can construct such B, right? So you have M1 and 2 and 3, and then you construct such B. Okay, you need to think a little bit and check that there's no logical inconsistent. Okay, so the claim is that you construct such B, and obviously that by definition, so you can check that so MIB 1 to n, basically given I, so given I, okay, there is always exists n such that MIB 1 to n is wrong. It's incorrect. Okay. Okay, so you can so basically this means that this UB is not in P to the B, right? Because P to a B, these are all the P to a B merge. These are all the P Turing machine with Oracle B. Okay, and what we show at least that there's always 1 to n, MIB or 1 to n is wrong. The reason is that for given I, right? So for given this mi, you run 1 to the n. for 2 to n steps, then I require that I brute force make mi on 1 to n is incorrect. Okay, and so I mean you may think it's very trivial that I just take whatever mi except 1 to n. That's make it incorrect, right? But I need to worry about that. Am I may query some strings in the previous, right? So when am I query some strings, then I just kill that strings. Okay, so make sure that that string is no, that string is different. That string is not in B. Okay, so which makes this proof very interesting is that yeah, so this proof is so this finish a proof. Okay, so given I, right? Yeah, or basically yeah. Okay, so this always is some n which it might be n is wrong. It's different from the results. It's different from different from it, right? Because mi always accept this is the same as down localization, right? For each I, right? For each I, right? For each I that for length 1 to n, you just do this. Okay, and yeah, okay. Okay, yeah, I think so. Yeah. Okay, so see you guys next videos.